Hey class, Mrs. Anderson here. I'm going to make a video for 5.6b. Don't have a ton of time here, so I'm going to try to do this as quickly as I can. So it's modeling using data points, and there's a lot to kind of go through here. But these are the calculator steps for when we did it with the graphing calculator, and we're going to use Desmos instead. So it's going to be a little bit easier. But you're going to enter your ordered pairs into your calculator, into a table, like an XY table on Desmos, and that makes a scatter plot. Then we want to decide if our points make a linear equation, so are the points trending more in a line? A quadratic equation, do they look more like kind of like a parabola? They have, one turn. Are they cubic? So cubic is similar to this. Does the data have two turns? Or quartic, that looks more like this. Does it have three turns, etc. So we're going to decide, is it linear, quadratic, cubic, or quartic? And then we use if it's linear, we use the correlation coefficient, but if it's not linear, we use the coefficient of determination. The closer it is to 1, the better the function, or the better the model fits the function or the data points. So we want the model that has the r² value that's closer to 1 and also fits the number of turns and fits our data the way that we want it to fit. So in order to do this, I've put together a Desmos sheet for you to use. So if you go into Schoology, go under our class Unit 5 folder, you'll see this polynomial regressions. So open that up, and we probably want to send that to Desmos or open in Safari. So I'm going to open that up in Safari. Then I'm going to split my screen here. So I'm going to also have that opened up, my Safari. So, whoops, I'm going to split my screen, and I want that here. I don't want it to be over top, I want it to split. Come on. Cooperate. All right, not going to cooperate for me. See if I just move my notes over here. So you can see this Desmos template has this all set up for you to put your data in here. So I'm going to put in my points now. So 0, move that notes for a second. 0, then 2, struggling, 4, 6, 8, and 10, and then put the y values in, 0.34, 0.35, 31. Okay, now I'm going to look at my picture here. I'm going to zoom in a little bit. This goes from x values. I'm going to hit this little wrench up here. I'm going to change my x value to just go from 0 to like 12. And then I'm going to change my y value, since I'm just looking at, numbers that are all less than 1. I'm going to look at just from 0 to 5. And I want them to count by maybe 0.5s. So I really get a better picture of this. So I can kind of see one small curve to start and then one curve down. So it doesn't look like linear. So this first one represents a linear regression. The r² value is 0.7. That's not very close to 1. It's not a straight line, that data, so I don't like that model. So I'm going to shut that one back off. Then I'll go down to my quadratic model and see that one seems to fit a little bit better. My r² is 0.85. It's closer to 1. but it's not a great model as well. My A value is negative, so that means it's going to go to negative infinity eventually. And this was a table of data that showed it was growth, increase in girth of a tree over a 10-week period. So a squared model doesn't make sense because the it's not going to go to negative eventually here. So let's look at the cubic model. This one is a little bit better. It has A values positive. My R squared is 0.191. So my R squared value is closer to 1. You can see the model matches the points better. It's got a good A value. I'd say that that would be a good model. My original picture had 2 turns in it. So 2 turns tells me it's usually cubic. It looks like the quartic model would fit as well. But if you look at this at the end here, the quartic model starts to rise and go to infinity a lot faster than the cubic model. So I think based off of just that, even though the R value is stronger, I think my cubic model fits better, especially because the original scatter plot had 2 turns in it. So I'm going to go with cubic. So then these A, B, C, and D, those are the coefficients of your line of best fit. So my line of best fit will be so sketch the scatter plot. That I just wanted you to make a little picture of what you're kind of seeing here. So it starts like this, kind of turns a little bit here, and then comes back up a little bit. Find the regression equation. So that is my y equals, my A value is my first coefficient, so 0.0007 x to the third, because I picked cubic. Then B comes next, so negative 0.014. Maybe I did 4 decimals, so maybe I'll do 4 decimals in this one too. So 0.138 x squared. Then it would be C, so plus 0.0494 x, and then D is last, plus 0.33. So I wish I could figure out how to get this to be bigger here. There we go. Okay. Of course, it went all the way down. Appreciate your patience. Here we go. A little bit better. Okay, so what is the correlation coefficient? I'm actually going to use the coefficient of determination, which is R squared, since it's a cubic model. So R squared was 0.9181. So we only use correlation coefficient for linear models. So otherwise we use coefficient of determination. All right, so let's do, I think I'm going to do one more. I'm going to skip example 2 and I'm going to do example 3. Because this is one where we have years. And so here I have years from 1960 to 1996. T equals 0 is the number of years since 1960. So in 1960, I'm going to plug in 0. 1965, that's 5 years. 1970 is 10. 1975, 15, 20, 25, 30, 35, and then 1996, right after 1995, would be 36 years. So I'm going to shut that back off, and I'm going to go back to my table, click on my last one, and then delete all the way back to my first spot. I'd start with 0, then in the Y, plugging in 9.7. So on my X's, I'm going to go 0 all the way up to, and then the last one, though, should be 36, not 40. Then 9.7, 9.8, 10, 9.6, 9.5, 10, 11.1, 11.8, and 11.8. Okay, so this time my scatter plot is up here, so I was able to zoom in to find it. You could again change your x's to match like 0 to 40 and then change the y's to be like 0 to 20 so you could see it a little bit better. So here I can see maybe 1 turn, 2, 3 turns almost. So I'm thinking linear is definitely out. This would not fit a linear model. So let's look at the quadratic model. It certainly doesn't look like a parabola, but you can see it doesn't really fit that model either very well because of the number of turns. Although the r squared value is high, which means that my predictions would probably work okay for my predictions because the coefficient of determination is strong there. But based on the number of turns, I don't feel strongly about the quadratic. So then I'm going to check cubic is even a stronger coefficient of determination with 0.94. It fits fairly well. Let's look at the x to the fourth instead. So it did have like 3 turns, so I thought x to the fourth would be better. Now this was the data was the average miles traveled per vehicle. So as you continue, the years go on, like if we were looking at 2000, you would say that the average number is trending up probably. And so, you know, in thousands, so I would guess that this is going to continue to increase, which means that my quartic model doesn't make sense because I have an a value that's negative. So all of a sudden at the end here, this model is dropping to a negative infinity. So I'm saying that, you know, after 1996, all of a sudden people just stop driving their cars. Well, that doesn't seem to make any sense. So that's why x to the fourth, even though the r squared value is bigger, it's closer to 1, 0.97 instead of 0.94, I would say the quartic model does not fit my data as well as the cubic model does, because here I'm saying, okay, after 1996, the people are continuing to drive their cars more, and it's getting exponentially bigger essentially. You know, the further on we go, I'd feel more comfortable using the cubic model, which means that so a sketch would just be, oops, a picture of this. So something kind of like, you know, a picture. The regression equation is when you plug in your a, b, c, and d into the equation, ax cubed plus bx plus c plus d. So your first coefficient is a, so 0.00013. I'm going to go 5 decimals so I can get enough of my a value. That'd be x to the third. Then b is negative, so minus 0. I'm going to stay consistent. I used 5, so I'm going to use 5 again. 1, 2, 3, 2. Actually, it would round up to just 3. And then that's x squared. Then c is your next coefficient, so plus 0.01581x. And then d is your last one, so d is your constant. So that would be the equation. What is the correlation coefficient? Again, we're using not a linear model, so we're looking at the coefficient of determination actually, which is my r squared value, and that is 0.9467. Predict the average number of miles traveled in the vehicle in year 2000. So I want to know when does t equal 2000 essentially. So 2000 is 40 years. If I subtract that, that's 40 years. And I'm actually using x for my variable for 2000. So I want to plug in when x equals 40. So what if I just plug in x equals 40 here, and I find when those 2 points intersect? or you could plug 40 into your equation. So plugging 40 in, I'm going to get the decimal 13.268, which really is in thousands, so it's in thousands. So that would be approximately 13,268 miles in the year 2000 is the average number of people are driving that. So that gave you a solid example here. You could probably stop now and be able to do your homework for the rest. I would definitely check out the notes for number 4C. I wrote some good notes on how you can find the answer to that. So it's similar to what I did with the x equals 40. Okay, thanks for watching. Hopefully that was helpful. Have a good night.